Hello everyone, welcome to another video on the transformation of random variables. So in the previous video we had taken a very simple example of transforming a random variable. Now let's increase the level of difficulty to a bit. Okay, so I'm taking the similar random variable x. I'm taking the same random variable x which I had taken in the previous video, where the probability density function f of x was defined as this, where it increased linearly from the range 0 to 1 and it stayed constant to a value 1 between the range 1 to 1.5. And in the previous video we had found out the cumulative distribution function of this random variable x, and we had found this to be capital F of x, which is this. Now let's take an example of a random variable y, where y equals x square. Now we have to find out the cumulative distribution function of y and the probability density function of y. So just like how I had explained it in the previous video, to find these values of the random variable y, we will follow the basic steps. So the steps are: first we find out the cumulative distribution function of x, which we have already found out, which is capital F of x, small x. Then using this we will find out the CDF of y, which would be this. And once we have found out the cumulative distribution function of the random variable y, then we will find out the probability density function of y by differentiating it. So you can just differentiate the CDF of y in order to calculate this one. Okay, now we already know the cumulative distribution function of x, which is defined like this here, and we know that this can also be written as p of capital X less than equal to small x. So all the probability of a random variable lying in a value less than x is this. It's denoted by the cumulative distribution function of x. Now we have to find out cumulative distribution of function of y. So we will write this in this manner: capital Y less than equal to all values small y, which is this. So how to convert it now? So how do I convert this into this similar form? So we will write y in form of x square as it was defined like this. So p of y less than equal to small y can be written as p of x square less than equal to small y. And since the value of x is always positive, like in the definition we didn't see any value of x which was negative, so it's a relatively simple case for us. We can also write it in this manner: p of x less than equals to root of y. So it's a simple case for us, as all values of x here are positive. Otherwise that wouldn't be the case. So we have to write it in this way. And you can also say that this is nothing but capital F of x, where we have given the input root of y. So we know that this was the cumulative distribution function of x. So what we can do is we can place this here, and similarly we can formulate the cumulative distribution function of y. So just replace this value square root of y in here, and you would know for the range where x small x lies between 0 to 1, the y would lie between this value. So y would also lie between 0 and 1. And we can write it in here, small y. So for the values of y being between 0 and 1, its value would be, if you just plug in the value of root y in small x here in this function, you would get, for the range this, you will get root y square by 2. This would be the value, and this is nothing but y by 2. So you will get a value y by 2 here. Now for this range where x lies between 1 to 1.5, the y would lie between this value. So y would lie between 1 to 2.25. So y greater than 1 and less than 2.25. If you just plug in the value which is mentioned here, square root of y, to this function, it would behave as square root of y minus half. So you can just put this here. So it would be square root of y minus half. Hence this would be the cumulative distribution function of y. And obviously for the values of y greater than equal to 2.25, this would be equal to 1. So now let's plot this and visualize the cumulative distribution function of y. So it would look something like this, where this is small y and this would be, take the value of this one, it would increase linearly from the values 0 to 1, as this is y by 2. Here at 1 it will take the value half, and then it would increase in a parabolic manner till the value of small y equals 2.25. And if you just plug in the value here, at y equals 0, this was 0, at y equals 1, this was half. Similarly, this also started with 1 minus half when y was 1, so this started with half and ended with 3 by 2 minus half, which is 1. So this parabola increases till the value of 1, and then it remains constant with the value of 1. So this would be the cumulative distribution function of y. Now, in order to find out the probability density function of our random variable y, we just need to differentiate this, and we would be able to find out the the probability density function of y. So we can say for the values where y is between 0 and 1, it's y by 2. So differential of y by 2 for by dy for the values of y lying between 0 to 1, and for the values of y lying between 1 to 2.25, it would be differential of root y minus half by dy. So this would be nothing but half, so I'm going to replace it with half, and this would become, since this is constant you can ignore it, this would become so here we have found out the cumulative the probability density function of small y. You can say its value is constant as half from the values 0 to 1, and then it decreases. So the value of this would decrease from half to where y is 2.25, it would be 1 by 2 times 1.5, which is 1 by 3. So this would decrease till 1 by 3 at small y equals to 2.25. Hence the probability density function of y looks something like this, where this is 1 by 3 and this is half. So I hope you like this video. Like, share and subscribe.